For centuries people imagined space as a passive backdrop, a Newtonian void where planets and stars simply moved, but modern science tells a very different story. Zooming into matter reveals that atoms are mostly empty space, with electron probability clouds surrounding tiny nuclei and vast regions that are anything but simple emptiness. Those regions are threaded with electric and magnetic fields, invisible structures that fill space and influence particles even when nothing seems to be there. Beneath those fields lie quantum fields, one for every particle type, filling all of space and vibrating even in the absence of matter. Even in their lowest state, these fields retain energy, a restless baseline called zero-point energy that makes the vacuum hum with activity. That hum shows up as virtual particles that briefly appear and annihilate, a constant flicker of creation and destruction at the smallest scales. One of the clearest laboratory signatures of vacuum activity is the Casimir effect, where two metal plates placed extremely close together feel a tiny push from the vacuum itself. The Casimir force can be explained simply: the vacuum modes between the plates are restricted, creating a pressure difference that nudges the plates inward. Einstein's insight that space and time form a single fabric changed everything, showing that space-time can bend, stretch, and carry energy just like any physical medium. Mass tells space-time how to curve, and curved space-time tells matter how to move, so space is not a passive arena but an active participant in dynamics. Quantum fields and curved space-time are two sides of the same coin, and understanding their interplay is one of the great challenges of modern physics. On the largest scales, the energy of empty space appears as dark energy, a mysterious pressure that accelerates the expansion of the universe. Astronomers discovered this accelerating expansion in the late 1990s, and the simplest explanation is that vacuum energy is pushing galaxies apart. But when physicists calculate the vacuum energy from quantum theory, the predicted value is staggeringly large, far larger than what we observe. This enormous mismatch between theory and observation is the cosmological constant problem, one of the deepest unsolved puzzles in physics. Some theories suggest the vacuum can exist in different phases, like water can be ice, liquid, or vapor, with each phase having different energy and physical laws. If our universe sits in a metastable vacuum, a transition to a lower energy state could in principle occur, creating a bubble that expands at the speed of light and changes physics inside it. Although vacuum decay makes for dramatic thought experiments, there is no evidence it is imminent, and if it ever occurred it would be undetectable until it reached us. The vacuum also shapes atomic structure. Electron clouds, energy levels, and chemical bonds are all influenced by the background quantum fields. Without vacuum fluctuations, the fine details of atomic spectra and chemical reaction rates would be different, and chemistry as we know it might not exist. Near a black hole horizon, the vacuum reveals another surprise. Quantum fluctuations can produce real particles, a process that leads to Hawking radiation. Hawking radiation slowly drains mass from black holes, showing that even the darkest objects are connected to the restless energy of empty space. When you gaze at the night sky, the darkness between stars is not empty. It is a seething ocean of fields and tiny events that shape the cosmos. Scientists probe this invisible activity with precision experiments and telescopes, from Casimir rigs in the lab to observations of distant supernovae and the cosmic microwave background. The more we study the vacuum, the more it appears to be the foundation of reality, a dynamic medium that underpins matter, forces, and the fate of the universe. If this journey through the hidden life of empty space intrigued you, like and subscribe for more cinematic explainers that turn the invisible into something you can almost see.